Let's take note of another important formula. This is the rate of change of grade, which we denote as r. For vertical curves, especially when we're using a 20-meter station interval, the formula is r equals a, L. Now, what do these terms mean? The value a represents the algebraic difference in grades. In simple terms, we just take the absolute difference between g2 and g1. On the other hand, L is the total length of the curve, expressed in meters. R is equal to absolute value of difference of g2 and g1 divided by n, where n represents the number of stations. So instead of using the total curve length directly, we're now expressing the change in grade per station. Now, to get the total length of the curve, we simply multiply the number of stations by the station length. Since each station is 20 meters, we have length is equal to n times 20. Alright, let's now move on to sample problem number 1. From the given situation, let's first identify and list down all the important values that we'll be using later. We are given a descending grade of 0.8%, which we'll assign as G1, and an ascending grade of 0.4%, which will be our G2. Now, take note, since G1 is negative and G2 is positive, this indicates that the curve transitions from a downward slope to an upward slope. Because of that, the vertical parabolic curve we are dealing with is a sag curve. The parabolic curve is said to connect at station 7 plus 020, which represents the location of the PVI, or point of vertical intersection. We are also given the rate of change of grade, which is 0.15% per 20-meter station. And finally, the elevation at station 7 plus 020, or at the PVI, is 420.60 meters. Now, let's move on to the first requirement of the problem, which is to determine the total length of the vertical curve. To do this, we'll use the rate of change of grade formula that we discussed earlier. We simply substitute all the given values that we have already identified. From the computation, we obtain the value of n, which represents the number of stations, and in this case, n is equal to 8. Now, to determine the total length of the curve, we multiply the number of stations by the station length. Since each station is 20 meters, we have L is equal to n times 20, then substitute n to 8, we will have 160. Now, let's proceed to the next requirement, which is to determine the elevation at the lowest point of the curve. But before we can compute the elevation, we first need to identify the location of that lowest point. To do that, we have to check whether the vertical curve is symmetrical or unsymmetrical. So, let's quickly review the given problem. We look for any information indicating unequal lengths on either side of the PVI. If the problem specifies different distances, then the curve is unsymmetrical. However, in this case, there is no indication of unequal lengths, and no data suggesting otherwise. So, in the absence of such information, we will assume that the curve is a symmetrical parabolic curve. We'll use the formula for the distance from the PVC to the lowest point, denoted as S1. S1 is equal to the G1 times L, divide them to the difference of G1 and G2. Just a quick reminder, be careful with the sign convention. Since G1 is negative and G2 is positive, we need to retain their signs during substitution. After computing, we obtain S1 is 106.6667 meters. So, the lowest point is located 106.67 meters from the PVC. Now, to better understand our solution, let's draw the parabolic curve so we can clearly visualize where the lowest point is located. First, we'll include the total length of the curve, which is 160 meters. Since we established that this is a symmetrical curve, we can divide it evenly, so we have 80 meters on the left side and 80 meters on the right side of the PVI. Next, we plot the location of the lowest point based on our earlier computation. As we can see, it falls along the right side of the curve. Now, to determine the elevation of the lowest point, first, we draw a reference triangle, then draw the height distance from the triangle to LP. The height of the triangle will represent y1, then y2 for the height from triangle to LP. Now let's visualize the triangle. y1 is the height, then the slope of the triangle is positive 0.4%. Determine first the base of the triangle. To determine the base of the triangle, which represents as x1, we may use the s1 then minus 80. So substituting the value of s1, x1 is equal to 106.6667 minus to 80. Then the answer is 26.6667 meters. Then from the reference triangle, using 26.6667 as the base value of the triangle. Recall first about the slope formula, which is equal to rise over run. Then, arranging the formula, rise is slope multiplied to run. We adopt this to the triangle. y1 is equal to the slope, 0.004, then multiplied to 26.6667. y1, therefore, is equal to 0.1067 meters. To solve for y2, we use the squared property of parabola. The x-coordinate distance to be used for y2 will be denoted as x2. To determine x2, it is equal to 80 minus x1, which is 80 minus 26.6667. Therefore, the value of x2 is 53.3333 meters. Now, using the squared property of parabola, y2 over the square root of x2 is equal to h over the square root of half of L, where h is the height of the curve. Since we still don't have the value of h, we need to compute it first. The formula for the height of the curve is equal to L over 8. Multiply them to the difference of g1 and g2. This formula is only applicable for summit curve. Instead, the formula of h for sag curve is equal to L over 8. Multiply them to the difference of g2 and g1. Just replace g1 to g2, then vice versa. Substituting the values to the formula of height of the curve for sag, it will be equated to 160 over 8. Multiply them to difference of 0.004 and minus 0.008. The answer will be 0.24 meters. Now, we can substitute the value of height if the curve to the squared property formula. y2 over the square root of 53.3333 is equal to 0.24 over square root of 80 meters. The value of y2 will be therefore is equal to 0.1067 meters. Then, going back to the illustration, we can determine the elevation of the lowest point of the curve by referring from the elevation at PVI, then go up through y1 and y2. The equation will be elevation at PVI plus y1 plus y2. Substituting the values, elevation of the lowest point of the curve is equal to 420.60 plus 0.1067 plus 0.1067. The answer will be 420.8134. The answer for elevation at the lowest point of the curve is 420.8134 meters. For the third requirement of the problem, which is to determine the elevation at station 7 plus 000, we need first to illustrate the curve to visualize the location of station 7 plus 000. Referring to the illustration, the location of the station 7 plus 000 is at the left side length of the curve. Now, the distance from station PVI, which is station 7 plus 020, to station 7 plus 000 is equal to 20 meters. Now, same solution from the previous, draw a triangle from PVI, then a line going to station 7 plus 000. The height of the triangle will be y3 and the height from the triangle to station 7 plus 000 will be y4. Now, analyzing the triangle, the slope is 0.8%, then the height is y3, and 20 meters for the base. y3 is equal to 20 times 0.008, then the answer for y3 is 0.16 meters. Now, we need the x distance for y4, which will be denoted as x4. Referring to the illustration, x4 will be equal to 80 minus 20, then the answer will be 60 meters. Using the squared property of parabola, the equation will be y4 over the square root of x4 is equal to h over the square root of half of L. Then, substitute the values of x4, h, and L. The value of y4 will be 0.135 meters. Now, referring to the illustration, elevation at station 7 plus 000 is equal to the elevation at PVI plus y3 plus y4. As we substitute the values, the equation will be 420.60 plus 0.16 plus 0.135. Therefore, the answer for the elevation at station 7 plus 000 is 420.895 meters. And that's it for today's lesson. If you found this helpful, make sure to review the example and try solving it on your own. Keep practicing, and I'll see you in the next video.